Hello, welcome to Electronics Education. I'm Vincent Chang. Today we are going to present the operational amplifier as a differentiator. Operational amplifier differentiator. Inverting differentiator. On the right-hand side, you see an inverting configuration, right? The closed loop transfer function is negative Z2 over Z1. So if we replace the Z1 by a capacitor and Z2 by a resistor, then you turn the inverting configuration into a differentiator. All right? So the closed loop transfer function of the differentiator is shown on the red highlight. So it's simply the Z1 is now 1 over SC. Z2 is replaced by R. So the answer is negative SCR. Negative SCR. So on the left-hand side is the differentiator. In the previous lecture, I presented the inverting integrator. Now it's on the right-hand side. So it's just the flipped, the interchange between Z1 and the Z2. Interchange between the R, C, the flipping position of the R, and the C. So the flipping the RC, then the result is actually the transfer function becomes what? Becomes the inverse to each other, right? So on the left-hand side is a negative SRC. But on the right-hand side is a negative 1 over SCR. So it's the strong contrast between the two, right? Between the two. So now let's move on to the magnitude frequency response, do the frequency domain analysis. So as usual, we define the omega 0 as the inverse of the time constant. So now it's SRC. It's the SRC. So 20 log omega. So positive 20 log omega. So which means on log scale, on log frequency scale, so it's going to be a straight line, right? And the slope is going to be 20 decibels. Slope is going to be positive per decade of frequency. And when omega equals omega 0, log 1 is the unity gain frequency for differentiator. So this is the frequency response for differentiator. So let me bring back the frequency response for the integrator. So you see the contrast, right? The strong contrast between the two. In the original circuit, so it's the interchange, it's the flip between R and the C. In the transfer function, you see another flip. Right? Differentiator negative SRC. The integrator is 1 over SRC. Of course, there's a negative sign. So on the magnitude response, you see yet again, another flip on the frequency axis, right? It's the mirror flip. It's the mirror 180-degree rotation, right? So this is very interesting and very important. So now let's see the time domain analysis. Do you still remember this? The capacitor voltage is what? It's the integration of current. And capacitor current is the differential, is the derivative of the capacitor voltage, like this. So now we need a current version. And let's bring back the differentiator circuit. So now VO equals what? VO equals negative I times R. And I equals the formula C dV dt. dV over dt, dV what V? The capacitor voltage. But because of the nature of the virtual ground on the inverting terminal, so VC, the capacitor voltage, is actually the input voltage VI. So now VO equals negative I1 times R. So now you see the VO is proportional to the derivative of the input signal. The derivative of the input signal is the differentiator. So now here's the takeaway. So which one is which? Which one is the integrator? Which one is differentiator? Well, let's start with the left-hand side. You see the negative 20, right? So this must be the integrator. Negative 20. And positive 20 log is positive 20 log. So the left-hand side is the integrator. The right-hand side is the differentiator. So what this frequency response tells you? What kind of information this frequency response you receive from this kind of frequency response? Do you know we seldom use the differentiator in the analog computation application? Why? In most of the occasion, the integrator is the most welcome. But we prefer not to use the differentiator, especially in the noise-rich environment. Because you see, for the integrator, let's say, it's just picture, if there's an environment has some high frequency noise, have some high frequency noise. For the integrator just is going to decline, it's going to reject those high frequency noise. So the higher frequency you go, the larger, the stronger attenuation decay you're going to receive, right? But so the integrator reject high frequency noise, but differentiator welcome, right? For the high frequency component, high frequency noise, the differentiator is going to welcome you and serve you with even bigger gain. So this brings us trouble. So differentiator is also named as a high frequency noise magnifier. Noise magnifier. So this very important nature, I hope you can remember. This is very, very important. And also the major takeaway of this lecture. In the next lecture video, I'm going to teach you about the low pass filter. See you in the next lecture. Thanks for watching.